Hello, welcome back to another video. Today we are starting Unit 2. This is the first lesson, Change in Arithmetic and Geometric Sequences. To start off, a sequence is a function from the whole numbers to the real numbers. This means that we are only able to plug in whole numbers such as 0, 1, 2, 3, 4, 5, etc. into a sequence, but we can get any real number as the output. So our outputs could be fractions, they could be decimals, they could be negative numbers, or just regular whole numbers. As a result, when we graph a sequence, we will have points, but we cannot connect them together to form a line or a curve. So since the input values are only whole numbers, and if you just think about how many numbers do you think exist between 1 and 2? If you just think of 1.5, that would be wrong. If you're thinking 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, etc., that would also be wrong. It's not that those numbers are not included. They are, but they are not the only ones. There is actually an infinite amount of decimals between 1 and 2. So even though in our mind, 1 and 2 are right next to each other, like how many numbers can there be? But if you think about all the little decimals, I can have 1.000000001, 1.0000002, 1.0000003, all the way until I get to 1.1. So even between 1 and 1.1, there is an infinite amount of decimals. So in the past, when we have points, we usually go and connect them. That will not be the case for sequences only because the inputs are only whole numbers. So you cannot connect these points together to form a line or a curve. Okay. Example 1, consider the sequence defined by a sub n equals 4n minus 3. These little things here are called subscripts. So when I read it out loud, I just say sub, and that just lets whoever is listening know that that is a subscript. Okay, so a sub n is equal to 4n minus 3. Find a sub 1 and a sub 7. So if you look at this subscript, it's going to be the same, it's in the same location as the subscript n. So that means that they're asking you, what is this function when n equals 1? And to find that, all you need to do is plug that n into the equation. Okay, so if I want to find a sub 1, I would do 4 times 1 minus 3. 4 times 1 is 4, and 4 minus 3 is 1. So that means that the first term in this sequence, so the subscript tells you which term you're at. Is it the first term, the second term, the third term, the fourth term, etc.? So this is saying that the first term in the sequence is 1. Okay, now they want us to find the seventh term, so that's a sub 7. So I would do the same thing. I would plug in 7 into n, so 4 times 7 minus 3. 4 times 7 is 28, and 28 minus 3 is 25. So that means that the seventh term in that sequence is 25. Okay. In this course, we will study two important types of sequences: arithmetic sequences and geometric sequences. Arithmetic sequences, their successive terms have a common difference or a constant rate of change. Successive just means, in consecutive order. First term, second term, third term, fourth term, just 1, 2, 3, 4, 5. So the numbers that are in order, they're going to have a common difference or a constant rate of change. We have found differences before. When we studied linear, quadratic, cubic, we said the first difference was linear, second difference quadratic, third difference cubic, fourth difference quartic. So it's going to be the same process. You're going to figure out, what do I need to add or subtract to get from one term in the sequence to the second term in the sequence, and from the second term to the third term, etc. If the numbers are all the same the first time, then that would be your common difference. So there's two formulas: a sub n equals a sub 0 plus d times n, or a sub n equals a sub k plus d times n minus k. I would recommend that you just remember this one. This one is the most versatile one. This one is only used if you're given a sub 0. Most of the time, you're not going to be given a sub 0. And even if you are given a sub 0, you can use this formula for any term. The 0 term, first term, second term, third term. So this one you're limited to if you are given the 0th term. And like I said, more often than not, you will not be given that information. So I would recommend just memorize the second formula. Okay, so a sub 0 represents the initial value. Sometimes if the problem is a real life problem, they might give you the initial value. But again, even if they give you the initial value, you can still use that second formula that I highlighted. Okay, D is going to represent the common difference. And a sub k is the kth term of the sequence. So that's just a random letter they picked. The k is just a placeholder. So again, if I say a sub 1, that just represents the first term in the sequence. If I say a sub 5, that's the fifth term in the sequence. A sub 10 is the 10th term of the sequence. Okay, so the subscript just tells you which term you are solving for. Arithmetic sequences behave like linear functions, except that they are not continuous. Again, you cannot connect these points together because you are only plugging in whole numbers. Increasing arithmetic sequences increase equally each step, and the slope always stays the same. I have an example here. A sub n equals 3n plus 1. I need to figure out what to put on this graph, so I need to come up with some points. The best way to organize this is to create a table. So my input values are usually x, but here my input values are going to be n. So instead of x, I'm going to put n. And my output, instead of it being y or f of x, now it is a sub n. So over here, I'm going to put a sub n, and a sub n is equal to 3n plus 1. Okay, now how am I going to select values for n? Remember that n is kind of the same thing as x, and this is the same thing as y. So if I'm trying to figure out values of n, I'm just going to use these that were given to me because this is the graph I was given. So there's no point in solving for 24 if my graph only goes to 8. There's no point in solving backwards either because my graph starts at 0. So I'm just going to do 0, 1, 2, 3, 4, 5. Okay, so all I have to do is plug these values of n. So again, this little subscript of n, I'm going to plug it into that n, and these are all my values of n. So I'm going to start 3 times 0 plus 1. Okay, 3 times 0 is 0, and 0 plus 1 is 1. 3 times 1 plus 1, 3 times 1 is 3, 3 plus 1 is 4. 3 times 2 plus 1, 3 times 2 is 6, and 6 plus 1 is 7. 3 times 3 plus 1, 9 plus 1 is 10. 3 times 4 plus 1, that's 12 plus 1, which is 13. 3 times 5 plus 1, that is 15 plus 1, which is 16. Okay, now that we have all the y values, you can figure out, do I have a common difference? So how do I get from one term to the next? Here I see that I need to add 3. I'm also adding 3 here, plus 3, plus 3, plus 3. So this is my common difference, and actually we were given this. So if you kind of think about this, this kind of resembles your y equals mx plus b. So remember that they said earlier that arithmetic sequences they behave like linear functions, and we know for linear functions the equation is y equals mx plus b. So the same way that the coefficient of the variable is your slope, this will also be your slope. The only thing is we're not going to use m because it's sequences. They said the common difference is represented with the letter d. So that means that d is 3, but this is still representing your slope. That is your common difference, how you get from one term to the next. And then usually b is the y-intercept, but here the initial value is represented with a sub 0. Graphically, this will be the y-intercept. If it was a real-life problem, that would be the initial value. Okay, so now we can actually plot these points on the graph. So we have 0, 1, 1, 4, 2, 7. The next one is 3, 10. I actually can't plot these because these y values are too large for my y-axis. I only go to 8, so this is all I can plot here. However, you can see that if you were to connect them, they would form that linear function. But again, you are not able to connect them, so you just leave it just like this. Okay, so let's try another problem. We're going to determine if these sequences are arithmetic, and if they are, we're going to determine the common difference. So when you're given an equation, you do have to create a table to find the actual points. So that's what we're going to do. So remember the input values are n, and then the values of s sub n, we're going to be plugging them into n squared minus 3. So these n values represent the subscript, which are going to be plugged into n squared. So again, we can just do 0, 1, 2, 3, 4, and we're going to have 0 squared minus 3. 0 squared is 0, and 0 minus 3 is negative 3. Next, we have 1 squared minus 3. 1 squared is 1, and 1 minus 3 is negative 2. 2 squared minus 3. 2 squared is 4, and 4 minus 3 is 1. 3 squared minus 3. 3 squared is 9. 9 minus 3 is 6. 4 squared minus 3. That would be 16 minus 3, which is 13. Okay, so let's see if there's a common difference. So to get from negative 3 to negative 2, I add 1. From negative 2 to 1, I have to add 3. To get from 1 to 6, I add 5. And to get from 6 to 13, I'm going to add 7. Because these are not the same number, there is no common difference, so this is not an arithmetic sequence. It is not arithmetic. There is no common difference. Okay? You could have actually just seen the equation. If you're well versed with your parent functions, you should know that anytime you have a variable that is squared and that is your highest degree, that's going to be a quadratic function. Okay, so this is actually a quadratic function, and we said that arithmetic behaves like a linear function, so there was no way it was going to go from a parabola to a line. So A is not arithmetic. Okay, let's try letter B. So again, we're going to create a table to organize our work, with the input value being n and the output value being s sub n. Again, all these values of n, we are going to be plugging them in, and I'm going to just select again 0, 1, 2, 3, 4. Okay, so we have 6 minus 2 times 0. PEMDAS says you have to do parentheses first and then multiplication, so we need to multiply 2 times 0 first, which is 0, and 6 minus 0 is 6. Next, we have 6 minus 2 times 1, which is 6 minus 2, which is 4. 6 minus 2 times 2 is 6 minus 4, and that is 2. 6 minus 2 times 3 is 6 minus 6, which is 0. And then we have 6 minus 2 times 4, which is 6 minus 8, which is negative 2. Okay, next we're going to see if there's a common difference. So to get from 6 to 4, I subtract 2. To get from 4 to 2, I subtract 2, minus 2, minus 2. Since they were all the same, that means that this is an arithmetic sequence. So it is arithmetic, and the common difference was negative 2. Okay, all right, moving on to the next one. Let me just move this over a little bit so I can have some more space. Okay, so these two are different in that they already gave you the numbers of the sequence, so you don't have to plug anything in, you don't have to create a table. All you're going to figure out is how do I get from one number to the next, okay? So to get from negative 7 to negative 2, I need to add 5. To get from negative 2 to 3, I add 5. To get from 3 to 8, you add 5, and this one you also add 5. So since they were all the same, that means that this is an arithmetic sequence, and the common difference is positive 5. Okay, let's try that again. To get from 1 to negative 2, I need to subtract 3. To get from negative 2 to 3, I add 5. To get from 3 to negative 4, I subtract 7. And to get from negative 4 to 5, I add 9. These are not the same numbers, so that means that this one is not arithmetic. Okay, let's go on to the next page. Example 3 says, let a sub n be an arithmetic sequence with a sub 3 equals 8 and d equals negative 3. Okay, so what we're going to do when you're given one term, you're going to label the subscript of that one term with the letter k because they use k in the equation. Okay, so the subscript is k, which is 3. What it is equal to is going to be a sub k, so that's the output. Okay, so remember, this is the input and this one is the output. So a sub k is 8 and the subscript is k. we are going to, one, find an expression for a sub n, and then we're going to find a sub 12. So this question is going to have two separate answers, okay? So the first thing is to write the formula. So we have a sub n is equal to a sub k plus d times n minus k, okay? So we're going to do a sub n is equal to 8 plus, the common difference was -3, and then we have n minus 3, okay? Now, to simplify this, you are going to distribute this -3 because we're following PEMDAS here, so we need to multiply before we do anything with this 8, okay? So that gives me 8 minus 3n plus 9. Now I need to combine like terms, so there's no other there's no other variable n, so I'm just going to leave -3n, but I do need to add these together, the 8 plus 9, and when I add those, I get 17. Okay, so this is one of my first answers, -3n plus 17. If you had written 17 minus 3n, that would also be correct. So you can flip these around if you want. I just write it like this because we're used to the mx plus b format where the slope is in the front. Okay, all right, now we need to use that to find a sub 12. So what we're going to do is plug in, instead of n, we're going to plug in 12 so we can find the 12th term. Okay, now remember parentheses first and then multiplication. So we're going to do -3 times 12, which is -36 plus 17. Okay, now when you add those together, you get -19. So the 12th term of that sequence is -19. Okay, example 4, let a sub n be an arithmetic sequence with a sub 2 equals 7 and a sub 6 equals 9. Find an expression for a sub n and use the expression to find a sub 24. Now this one is different than the previous example because the previous example gave us the common difference. This one did not, they just gave us two terms. So when you are not given the common difference, you do have to find it yourself. So I'm going to tell you the steps. So when you're given two terms, you're going to label the smaller subscript as k and the larger subscript as n. When you are done with that, when you find the common difference, you are going to proceed with k only. Do not use n again. Okay, so let me explain now that we're going to do some examples. Let me write this again. My pen is still glitching a little bit. Okay, so between these two terms, the smaller subscript between 2 and 6 is 2. So I'm going to label k as 2. That means that this corresponding 7 will be my a sub k because they go together. So if this is k, then this also has to be k. My larger subscript was 6, so I'm going to label that as n, and the corresponding output would have to be a sub n because these always have to match and these two go together. Okay, so now we're going to write the formula. The more you write this formula, the more you'll remember it. So I'm going to write it in every single problem. I recommend you do the same when you're doing your homework or any practice at home, because remember that on the AP test, you are not going to have a formula chart. So it is important that you remember this formula. Okay, so now we have 9 equals 7 plus d times 6 minus 2. All right, we have to do parentheses first, so we're following PEMDAS, so we're going to leave everything as is, and now we have 6 minus 2, which is 4. Okay, now I'm going to subtract 7. 9 minus 7 is 2, and d times 4 is the same thing as 4d. Now I need to divide by 4. These cancel out, and now d is equal to 1/2. Okay, so now that we have the common difference, I'm going to rewrite the formula. And like I said earlier, once you find d, you're going to proceed with k. So pretend that this is not here. Please do not plug it in again. You are just going to plug in the first point we were given. Okay, so I'm going to say a sub n is equal to 7 plus 1/2 times n minus 2. All right, and just like before, we're going to distribute this 1/2. So we get 7 plus 1/2 n. Now, if you don't know how to multiply fractions, what you can do is whenever you're multiplying a fraction by a whole number, is to turn the whole number into a fraction by putting it over 1. Okay, so then it becomes 2 fractions. Okay, let me do this on the side so you can see what I'm trying to show you. So 1/2 times -2 over 1. And when you multiply fractions, you just multiply straight across. So 1 times -2 is -2, and 2 times 1 is 2. And when you divide those together, you get -1. Okay, so over here, I'm going to write -1. And just like before, you're going to combine your like terms. So when you write your answer, you'll put a sub n is equal to 1/2 n. And then 7 minus 1 is positive 6. So this is our first answer. They said find the expression for a sub n. Okay, now the next step, they wanted us to find a sub 24. So we're going to plug in 24 into n. Okay, and then again, if you struggle with multiplying fractions, you're going to do 1/2. And you can turn that 24 into a fraction by putting it over 1, and then you multiply straight across. So 1 times 24 is 24, 2 times 1 is 2, and then 24 divided by 2 is 12. So this becomes 12 plus 6. So the 24th term of this sequence is 18. Okay. So here's example 5. Example 5 looks a little bit different because you're given a graph, but it's actually going to be the same exact steps as we did in example 4. We were not given the common difference. The only difference is that here we were only given 2 points. And if you look here, we were given 1, 2, 3, 4, 5 points. But it's going to be the same thing. All you need to do is select 2 points. Any 2 points that you want are going to work. I'm just going to select 1, 6 and 2, 4 as an example. Okay, so remember that the n is your input, which is the same thing as your x, and then a sub n is the output, which is the same thing as y. So whenever you're trying to figure out which one you're going to label as k or which one you're going to label as n, you need to look at the x values. So between the x values 1 and 2, 1 is the smaller k value, so I'm going to label this one as k. That means that the corresponding y value is a sub k. The bigger x value was 2, so that's going to be my n, and the corresponding y value is a sub n. Okay, so I'm going to write the formula now. A sub n is a sub k plus d times n minus k. And when I plug everything in, I get 4 equals 6 plus d times 2 minus 1. Okay, so now I need to simplify my parentheses first. So that gives me 6 plus d. 2 minus 1 is just 1. So now we get 4 equals 6, and then d times 1 is just d. Now I subtract 6. 4 minus 6 is -2. So my common difference is -2. Okay, now I can write my formula again. A sub n is a sub k plus d times n minus k. And remember, for the second step, you are going to ignore this one. You're only going to plug in the first one. So we have a sub n is equal to 6 plus the common difference, which was -2, times n minus 1. Now, like always, we're going to distribute this first. So we get 6 minus 2n plus 2. Just like before, you're going to combine your like terms, which are 6 and positive 2. So a sub n is negative 2n plus 8. Okay, and then they wanted us to find a sub 17. So I'm going to do negative 2 times 17 plus 8. This would be negative 34 plus 8. So the 17th term is negative 26. Okay, so that's all for arithmetic sequences. Now let's try geometric sequences. Okay, geometric sequences have successive terms that have a common ratio or a constant proportional change. The formula for the common ratio is y2 divided by y sub 1. You're not going to use that every single time, but it is helpful to remember it, especially when the common ratio is like a fraction, because you can't really multiply fractions in your head. I mean, you can, but most of us are not able to just off the top of our head be like, oh yeah, that's multiplying times 2/3 times 2/3 times 2/3. So if it's easy, like times 3 times 3 times 3, or times 2 times 2 times 2, those you don't need the formula for, but you'll see some examples where using the formula will be helpful. Okay, just like in arithmetic sequences, I really only need you to remember this second formula. Again, you're almost never going to be given the initial value g sub 0, but g sub 0 is the initial value, r is the common ratio, and g sub k is the kth term of the sequence. And these all have g's because g for geometric. Okay, geometric sequences behave like exponential functions except that they are not continuous. Increasing geometric sequences increase by a larger amount each step, and the percent of increase always stays the same. All right, so here we have g sub n equals 8 times 1/2 to the power of n. So just like in arithmetic, we're going to create a table, and we're going to select the values of n and plug them in. Okay, so these values of n are going into the subscript and the exponent. I'm just going to select 0, 1, 2, 3, 4, and 5. This pen really sucks, I'm sorry. And 5. Okay, so we have 8 times 1/2 to the power of 0. Now for PEMDAS, you need to do the exponents first before you multiply by 8. So I'm going to carry the 8, and anything to the power of 0 is 1. 8 times 1 is 8. Now we'll do 8 times 1/2 to the power of 1. Again, carry the 8. 1/2 to the power of 1 is still 1/2. Anything to the power of 1 is itself. Now, if you struggle with multiplying fractions, put your whole numbers like this 8. I'm going to bring it up and I'm going to put it divided by 1. Because now I can do 8 times 1. When you multiply straight across, you get 8, and 1 times 2 is 2. And I know that 8 divided by 2 is 4. Okay, let's do 1/2 squared. So again, you're going to carry the 8. Now, when you have a fraction raised to an exponent, you need to apply that exponent to the numerator and the denominator. So you're going to have 1 squared divided by 2 squared. So I'm going to put 8 over 1, and then 1 squared is 1 and 2 squared is 4. So if I multiply straight across, I get 8 over 4, which I know is 2. Let's try that again. 8 times 1/2 cubed would be 8 times 1 cubed over 2 cubed. So if I do 8 over 1, 1 cubed is 1 and 2 cubed is 8. If I multiply straight across, I get 8 over 8, which equals 1. Now we can do 8 times 1/2 to the power of 4 would be 8 times 1 to the 4th power and 2 to the 4th power. Okay, so we have 8 over 1, and then 1 to the 4th power is 1, and then 2 to the 4th power. Let's write some powers over here on the side. Okay, so these are going to be helpful to memorize. 2 squared is 4, 2 cubed is 8, and then all you're doing to go from one to the next is multiply by 2. Okay, so 8 times 2 is 16. So if you do that again, 2 to the 5th power, 16 times 2 is 32. 2 to the 6th power would be 64. 2 to the 7th power would be 128. 2 to the 8th power would be 256. 2 to the 9th power would be 512. 2 to the 10th power would be 1024. Okay, and you can keep going, just multiplying by 2 times 2 times 2, right? 4 times 2, 8, 8 times 2, 16, 16 times 2, 32, 32 times 2, 64, etc., etc., times 2 times 2 times 2 times 2. Okay, so if you memorize these, it'll make your math a lot quicker. But if not, you can always just make a little chart and figure out the exponent that way. Okay, so we were looking for 2 to the 4th power, which is 16. So this will be 16 here, and then if I multiply straight across, I get 8 over 16. Now I know that both of these are divisible by 8. So if I divide 8 divided by 8, I get 1, and 16 divided by 8 is 2, so this becomes 1/2. Okay, last one, 8 times 1/2 to the 5th power would be 8 times 1 to the 5th power divided by 2 to the 5th power. So I get 8 over 1, and then 1 to the 5th power is 1, and on our chart, 2 to the 5th power is 32. So we have 32 here, and now we get 8 over 32. Now these are also divisible by 8, so I'm going to divide both of them by 8, and I get 1 over, and then 32 divided by 8 is 4. Okay, so now we can plot these on our graph. So 0, 8, 1, 4, 2, 2, 3, 1, 4, 1/2, 5, 1/4. And if we continue this pattern, we would get 1/4, and then 1/8, and then 1/16, and then 1/32. And they just get smaller and smaller. But they're not going to equal 0. They're just going to get really, really close to 0. And if you can see, if you were to connect them, this graph would be an exponential decay graph. We're actually going to go into more detail about exponential functions very, very soon. But remember that with sequences, you cannot connect the points together. So we're going to leave the graph like that. Now, another thing here that I want to mention is how do we get from 8 to 4, and from 4 to 2, and 2 to 1, and 1 to 1/2, and 1/2 to the power of 4. So I know that your mind is probably thinking we divide by 2, divide by 2, divide by 2. And yes, that is true, but for sequences, you need to have a multiplier. So I need you to remember that dividing by 2 is the same thing as multiplying by 1/2. So these are all being multiplied by 1/2. Okay, so dividing by 2 is the same thing as multiplying by 1/2. Similarly, dividing by 3 is the same thing as multiplying by 1/3. Dividing by 4 is the same thing as multiplying by 1/4, and so on. So whenever you're looking for the common ratio, make sure it is a multiplier and not something that you are dividing, okay? And then actually the formula here, what is in parentheses, represents your common ratio, which they had actually told us it was 1/2. You didn't know what that meant yet, but this is that it's 1/2 because you multiply 1/2 to get from one term to the next. Okay, so Let's do some more examples. We're going to determine if these are geometric, and if they are, we're going to figure out what the common ratio is. So just like in the first page, we're going to create a table here, and we're going to get the y values to see if they have a common ratio. So I'm just going to pick 0, 1, 2, 3, 4, and I'm going to do 3 times 0 squared. You have to do the exponents first. 0 squared is 0, and 3 times 0 is 0. Next, we do 3 times 1 squared. 1 squared is 1, and 3 times 1 is 3. 3 times 2 squared. 2 squared is 4, and 3 times 4 is 12. Next, you do 3 times 3 squared. 3 squared is 9, and 3 times 9 is 27. Next, you do 3 times 4 squared, which is 3 times 16, which is 48. Okay, so let's see if there's a common ratio. We're going to be using the little formula I gave you earlier, which is dividing the y values. When I do the common ratios, I like to start at the bottom because it makes it easier for me. So I'm going to divide the second one, which is the one underneath, divided by the first one, which is the one on top. And then I'm going to continue in that fashion. So this one is 27 over 12. This one is 12 over 3. And this one is 3 over 0. Okay, so now that I have all these fractions, so you might be thinking to yourself, well, they're not the same. This is not geometric. Sometimes it appears that way, but you do still need to reduce the fractions, because sometimes when you reduce the fractions, they do end up being the same. Okay, so the first fraction I have is 3 divided by 0. Well, remember that 0 on the top is okay, but 0 on the bottom is a no-no. So this is important for you to remember as well. When you have 0 at the bottom, it will be undefined. You are not able to divide by 0, okay? And then 12 divided by 3 is 4. And then you can keep going, but they're already not working. So I'm going to say this one is not geometric. Okay, so remember, they all have to be the same number for it to be geometric, and these were not. So let's try it. And then also, if you look at the formula, this was 3n squared, which would have been a parabola, which would be quadratic. And they said that geometric behaved like exponential functions, so that wouldn't have worked anyway. Okay, so let's look at this one. Again, I'm going to create a table. We have n and then s sub n, which is 4 times 2 to the power of n minus 1. So I'm going to pick 0, 1, 2, 3, 4. And then we're going to do 4 times 2 to the power of 0 minus 1. We need to subtract those exponents first, so I would get negative 1. Okay, now I still need to take 2 to the power of negative 1. Okay, so in Algebra 2, you were taught this property. Most of my kids did not remember this, but it is called the negative exponent property, or the negative exponent rule. And basically all it says is if you have a base, such as a raised to a negative exponent, all you need to do is take the reciprocal. Okay, so remember that all whole numbers are divided by 1. So if you take the reciprocal, it would be 1 over, but once you put this in the denominator, you are no longer going to put the negative exponent, it'll just be a positive exponent. Okay, so I'm going to apply that property here. So I'm not going to use the 4 yet, because that's the last step in PEMDAS, is multiplication. I first need to worry about this exponent, 2 to the power of negative 1. So if I take the reciprocal, I'm going to have 1 in the numerator, the base is 2, and the exponent was negative 1. But if I put it in the denominator, it'll now be a positive 1. Okay, and then so if I multiply, I can convert that 4 into a fraction by putting it over 1. And then 2 to the power of 1 is just 2. So if I multiply straight across, I get 4 over 2, which is just 2. All right, moving on, we have 4 times 2 to the power of 1 minus 1, and 1 minus 1 is 0. I first need to do 2 to the power of 0, and I know anything to the power of 0 is 1, and 4 times 1 is 4. Next, we have 4 times 2 to the power of 2 minus 1. 2 minus 1 is 1. Anything to the power of 1 is itself, and 4 times 2 is 8. Now we have 4 times 2 to the power of 3 minus 1, which is 4 times 2 squared, and 2 squared is 4, and 4 times 4 is 16. Okay. Next we have 4 times 2 to the power of 4 minus 1. 4 times 2 cubed, where 2 cubed is 8, and 4 times 8 is 32. Okay, so let's see if there's a common ratio. So I'm going to start from the bottom and do 32 over 16. Then I'm going to do 16 over 8. Then I'm going to do 8 over 4. And then I'm going to do 4 over 2. Okay, so now let's see if these reduce to the same number. 4 divided by 2 is 2. 8 divided by 4 is 2. 16 divided by 8 is 2. And 32 divided by 16 is also 2. So that means that this one is geometric. So this one is geometric, and the ratio R is equal to positive 2. Okay, so let's move on to the next problem. So we have 1, 3, 2, 6, 4, 12, 8, and 24. Okay, so what I'm going to do is again do my little fractions. I'm going to do a different color so you can tell it apart from my other work. So I start with the last one and I divide it by the previous one, and then I keep going in that fashion, dividing the second one by the first one. Okay, so if I were to simplify these, 3 divided by 1 is 3. 2/3 cannot be reduced. 6 over 2 is 3. 4 over 6 reduces to 2/3. 12 over 4 reduces to 3. 8 over 12 reduces to 2/3. And 24 over 8 reduces to 3. So even though there is a pattern, it is not the pattern that we need. For it to be geometric, they have to be the same exact number every single time. It cannot go back and forth between the same two numbers, okay? So this one is not geometric. Let's try D. So again, with the fraction, I'm going to start on the back and then divide it by -2, -2 over 4, 4 divided by -8, and -8 divided by 16. If I reduce these, -8 over 16 becomes -1/2. This is -1/2, -1/2, and this one was already -1/2. So that's why it's important to reduce your fractions. If you had left it like this and you didn't realize that they all reduce to -1/2, you might make the mistake to say they are not geometric, but they are geometric because the common ratio was always -1/2. Okay, so let's do an example. Let G sub n be a geometric sequence with G sub 1 equals 12 and R equals 2. So just like with arithmetic, when you're given one term, you're going to label the subscript with K. So K is 1, and the output would be G sub K, which is 12. And this one, they gave us the common ratio. So we have G sub n is G sub K times R to the power of n minus K. So I'm going to put G sub n equals 12 times 2 to the power of n minus 1. Okay? And even though it looks ugly, this is the final answer. You cannot multiply 12 times 2. That would be against the order of operations. So if you were to think about it, when we did these here, remember that we always simplified the exponent first, right? We did 2 minus 1 is 1, and then we did this. And the very last step, notice that the 4 was in every last step. So the very last thing we did was 4 times 2, 4 times 4, 4 times 8. So that's the same thing here. first you're going to do the exponent, then you're going to take 2 to that exponent, and finally you're going to multiply by 12. So it would be incorrect if you try to do 24 to the power of n minus 1, because it would be against the order of operations. So even though it doesn't look too nice, this will be the final answer. Okay? And now they want us to find g sub 4. So to do that, you're going to plug in 4 into the exponent. Okay? And then 4 minus 1 is 3, and 2 cubed is 8, and 12 times 8 is 96. Okay, so the fourth term here is 96. Okay, and then notice how we did all the exponents first. So that's what I was saying. You first do 4 minus 1, then you get 3. Then you do 2 cubed and you get 8. And the very last thing you do is multiply by 12 to get your final answer. So that's why it's important that you do not multiply too early, okay? Because that should be your very last step. All right, in the example 8, we're given a graph with several terms of the sequence, and it's going to be the same thing as we did in arithmetic, where you're just going to select 2 points, whichever 2 points that you want. I'm just going to use 1 and 4 and 2, 2. The smaller x value, the smaller input will be with k. So this is k is 1 and g sub k is 4, and then this one would be n. So n is 2 and g sub n is 2. Okay, so I'm going to write the formula. G sub n is g sub k times r to the power of n minus k, and I plug everything in. I get 2 equals 4 times r to the power of 2 minus 1. Now we have to do exponents first. So I'm going to do 4 times r and then 2 minus 1, which is 1. And then anything to the power of 1 is just itself. So we just have 4r. And then you divide by 4. So r is equal to 1/2 because you reduce the fraction. Okay? Now we're going to write the expression. So g sub n is g sub k r to the power of n minus k. Remember that on the next step, you no longer use n. So we have g sub n is equal to 4 times 1/2 to the power of n minus 1. Okay, so that's the expression. And now we're going to use that expression. I'm going to go to the other side and we're going to find g sub 10. So we're going to do 4 times 1/2 to the power of 10 minus 1, where we're going to first subtract 10 minus 1, which is 9. Remember that when you have a fraction raised to an exponent, you need to put the exponent on both the numerator and the denominator. Okay? Now, I'm about to multiply a whole number by a fraction, so if it helps you to put your 4 divided by 1, 1 to the power of 9 is 1, and 2 to the power of 9, we did write this earlier, so I'm going to scroll up to the top of my page. 2 to the power of 9 is 512. Okay, so that's why it comes in handy to make sure that you know your exponents. Otherwise, you would have been sitting here doing 2 times 2 times 2 times 2 times 2 times 2, etc., etc., and then 4 times 4 times 4, and then 16 times 16, and it takes a lot of time. Okay, so it's in your benefit to remember as many as you can from memory, and if you cannot memorize them, then just know how to get them quickly, because all you're doing is times 2 times 2 times 2 times 2, but like quick. Okay, so if you multiply straight across, you get 4 divided by 512. I feel like these are going to be divisible by 4, so let's test it out. 4 divided by 4 is 1, and then 512 divided by 4. So remember, on the AP test, you're not going to have a calculator, so you are expected to know how to do this elementary math by hand. So how many times is 4 going to 5? Just one time. So now we have 5 minus 4, which is 1. I'm going to bring down this one. Now I have 11. 4 times 2 is 8. 11 minus 8 is 3, and then I'm going to bring down this 2. And then 4 times 8 is 32, and then I get no remainder, which means this is perfect. So I have 128 here. So that means that the 10th term of this sequence is 1 over 128. Okay, let's go on to the last page. Reminder, a geometric sequence has successive terms that have a common ratio r. This means that each term is multiplied by the same number to generate the next term. The general form of a geometric sequence is usually the best form to use, which is the one that I had told you to highlight on the previous page. G sub n equals G sub k times r to the power of n minus k. Example 1, find an equation for the geometric sequence with G sub 3 equals negative 3 and r equals 10. Okay, so we have one term, so I know that one term I'm going to label as k and G sub k, where the input is the subscript and the output is the y value. Okay, so I'm going to write the formula. G sub n is G sub k. Notice that I'm rewriting it even though I have it right here. The reason I'm doing that, and I want you to do it, I have this formula memorized, okay? But this is the first time you're exposed to it. The more you write it over and over again, the more you're going to remember it, okay? Just relying on it being printed on the page is not going to help you when you have a quiz or a test or when you're sitting in the AP exam, okay? So now I have G sub n is equal to negative 3. Let me start over. This looks so bad. Equals negative 3. The common ratio was 10, and we have n minus 3. And this is the final answer. Okay. They did not ask us to find a term, so that's it. That answers the question. Okay. So here we have another example where we're given one term. So I'm going to label the subscript as k and the output as G sub k. And they gave me the common ratio. So now I'm going to write the formula. And I'm going to plug in G sub k, which is 24. The common ratio was 1/2, and the exponent will be n minus 2. So that's my expression for G sub n. And now they want me to plug in G sub 5. So I'm going to do 24 times 1/2 to the power of 5 minus 2. Remember, you always have to do your exponents first. So this is the same, and then the exponent 5 minus 2 becomes 3. And when you have a fraction raised to an exponent, you have to apply the exponent to the numerator and the denominator. So now I get 24, and I'm going to go ahead and put this over 1 so I can multiply it easier. 1 cubed is 1, and 2 cubed is 8. When you multiply straight across, you get 24 over 8, which equals 3. So the fifth term of this sequence is 3. Okay. The examples above were relatively quick and easy because we were given one term of the sequence and the value of r. However, how can we deal with problems that give us two terms but not the value of r? I already gave you these instructions on the second page of the arithmetic sequences, so it's going to be the same exact thing. When you're given two terms, you're going to label one as k and the other, use the larger k as the n. Okay, so you're going to use the smaller subscript as k, the larger subscript as n, and it's going to be the same thing. You'll see. Okay, so here I have two terms. One has a subscript 3, one has a subscript of 6. So the smaller one I'm going to label as k, so the corresponding output is G sub k. So the larger subscript will be n, and the corresponding output would be G sub n. So first I need to find r. So I'm going to first write the formula so I can plug in all of this information, and then I'm going to work backwards to solve for r. So I have 128 is equal to negative 2 times r to the power of 6 minus 3. So I'm going to simplify the exponent first. 6 minus 3 is 3. Next, I need to divide by negative 2. So these equal 1, they cancel out. I'm going to come up here, 128 divided by negative 2 is negative 64. Okay, and this is equal to r cubed. To get rid of the power of 3, you need to do the cube root. And then the cube root and the cube cancel out. Okay, now we have the cube root of negative 64. Now, you might remember me telling you earlier that you cannot take the square root of a negative number such as negative 36. I told you that this was equal to plus or minus 6i because of the negative inside. And that is true for even roots. So if you had square root, fourth root, sixth root, eighth root, etc., you get an imaginary I. But when you have an odd root like 3, 5, 9, 7, you can have a negative on the inside. It just means that your answer will be negative. So that is perfectly okay. All right, so how are we going to get the cube root of negative 64 without a calculator? Okay, I'm going to go back up here and I'm going to add on to these powers that we had. But now, so we did a bunch of 2's. Let's see 3's because we're trying to find the cube root. So that cube root lets me know that my base is going to come from, well, never mind. Let me just start over. Okay, let's just practice the bases of 3. So 3 squared is 9. 3 cubed would be 3 times 3 times 3, which is 27, or just 9 times 3. And then 3 to the power of 4 would be 81. So those are just some common ones. Now we can do, let's practice the 4's. So 4 squared we know is 16, and 4 cubed is 64. And if you multiply that by 4 again, 64 times 4 would be 256. Okay, so our problem was asking us the cube root of negative 64. So what that means is that we're looking for 3 numbers that is the same exact number that when you multiply them, you get 64. So it has to be the same exact number, okay? 3 times. So if I look here, I have 64 here, but that's to the power of 6. So that means it's 2 times 2 times 2 times 2 times 2 times 2. So it's not 3 times. But if I look here, I have another 64, and it's telling me that 4 times 4 times 4 is 64. So I'm looking for 3 numbers that multiply to 64, and those 3 numbers are all 4. Okay, so that's why it's important to know these exponents here and that you're able to replicate them quickly so that you can do these calculations without the use of a calculator. So when I ask you what is the cube root of negative 64, all you're looking for again is 3 numbers, and it's 3 because it's cube root. So that lets you know it's something cubed, okay, that equals negative 64, and it is 4. But I have to make it negative because it was a negative 64. Okay, now let's write the formula. G sub n is G sub k times r to the power of n minus k, where G, and then remember on this second step, you are not going to use this one again. So we have G sub n is equal to negative 2 times negative 4 to the power of n minus 3. Okay, and now they want us to find G sub 11. So I'm going to do negative 2 times negative 4 to the power of 11 minus 3, which is negative 2 times negative 4 to the power of 8. Negative 4 to the power of 8. Okay, now how far did we get on our exponent for 4? We just got to 4 to the 4th power. 4 cubed, 4 squared. So we don't have all the way to 4 to the power of 8, but we know that for sure negative 4 cubed is negative 64. And if I do another negative 4 cubed, that's another negative 64. Okay, now the law of exponents tells me if I have the same base, which I do, the base is negative 4, I can just add the exponent. So far I have 6, but I need 8. So that means I need to do another 2. And I know that negative 4 squared is positive 16. So since they all have the same base, which is negative 4, I just need to add these together. So 3 plus 3 is 6, and 6 plus 2 is 8, and 8 is what I'm looking for. So if I just multiply all of these together, it'll be the equivalent of negative 4 to the power of 8. Okay, so I'm going to do that on the side. I know already that these two negatives are going to make a positive. Okay, so 64 times 64. 4 times 4 is 16. 6 times 4 is 24, plus 1 is 25. On the next line, you bring down a 0. 6 times 4 is 24, and 6 times 6 is 36, plus 2 would be 38. Now I'm going to add these. You get 6, 9, 10. Bring up the 1. Now you get 4. So again, these two negatives make a positive. So I have positive 4096, and I still need to multiply that by 16. So I'm going to do times 16. 6 times 6 is 36. 9 times 6 is 54. 54 plus 3 is 57. 6 times 0 is 0. 0 plus 5 is 5. 6 times 4 is 24. And I'm going to come back down, add a 0. 1 times 6, 6. 1 times 9, 9. 1 times 0 is 0. And 1 times 4 is 4. And I'm going to add these up. I get 7. 13, bring up the 1. This is 15, bring up the 1, 5, and then 6. Okay, so when I come back to my problem, I have negative 2, and I found out that negative 4 to the power of 8 is 65,536. Okay, now we are not done because we still have to multiply that by a negative 2. So I know that my answer is going to be negative. So now let's do 65,536 times 2. 6 times 2 is 12. 2 times 3 is 6 plus 1 is 7. 5 times 2 is 10. Bring up the 1. 5 times 2 is 10 plus 1 is 11. Bring up the 1. 6 times 2 is 12 and plus 1 is 13. So my answer is negative 131,072 is the value for G sub 11. Now you might be thinking, oh my gosh, this is so much work. Why don't we get a calculator? It is not our fault. We did not design this test. It's just the nature of the course, and it's pretty easy multiplication. Yes, it is tedious, but it is not impossible, and you were taught how to multiply in elementary and middle school. So on the AP test, they will be expecting you to know how to do basic math by hand, even if it is a lot of work like we just did. Okay. So anyways, last problem, let G sub n be a geometric sequence with G sub 2 equals 48 and G sub 7 equals 1.5. So again, the smaller subscript I'm going to write as k, and the output would be G sub k. The bigger subscript is n. Now this 1.5, I'm going to write it as a fraction. So I know most of you guys are afraid of fractions, but believe it or not, multiplying and dividing with fractions is a lot easier than dividing and multiplying with decimals. Okay, so just take my word on that for now. I'm going to show you. We have G sub n is G sub k times r n minus k. I'm going to plug in everything, so I get 3 over 2 is equal to 48 times r to the power of 7 minus 2. If you subtract 7 minus 2, you get 5. Now we need to divide 48. Okay, now you're like, well, okay, now what? Now how do I divide fractions? Okay, you're going to do keep, change, flip. So I'm going to write this down so that when you look back at your notes, you know what we did. And basically all this is you're going to keep the top, change the sign, flip the bottom. When you do keep, change, flip, I recommend that you have a numerator that's a fraction and a denominator that's a fraction. Right now our denominator is not a fraction, so I'm just going to put it over 1 to make the next step easier. Okay, so again, I'm going to keep the top, which was 3 over 2. I'm going to change the sign to multiplication, and I'm going to flip the bottom around so I get 1 over 48. And this is equal to r to the 5th power. Okay, if you multiply straight across, you get 3 over 96, which is equal to r to the 5th power. Okay, now I ran out of space, so I'm going to come over here. These two are divisible by 3. So if I do 3 divided by 3, I get 1, and 96 divided by 3 is 32. And again, this is equal to r to the 5th power. To get rid of the power of 5, you need to do the 5th root. When you have to do the root of a fraction, Without a calculator, you need to do that root separately to the numerator and the denominator, okay? Now this fifth root and the power of 5 cancel out. The fifth root of 1 is just 1, because 1 times 1 times 1 times 1 times 1 is still 1. And then what is the fifth root of 32? So again, you're looking for 5 numbers, 1, 2, 3, 4, 5, that when you multiply them together, you get 32. Okay, now earlier we talked about it, so you can go back into your page, but basically it's 2 times 2 times 2 times 2, because 2 times 2 is 4, this is 4, this is 2, this is 16, and 16 times 2 is 32. Okay, so when you're now to avoid doing all that work, it's easier if you just memorize the exponents like I've been saying, but if not, you can always write it out and think about it, even though it's going to take you a little bit more time. Okay, so r is equal to 1/2. Now I'm going to write the formula. G sub n is G sub k times r to the power of n minus k. And on the second step, you are not going to use this n. You're only going to use k. So we have G sub n is 48 times 1/2 to the power of n minus 2. So this is the expression for G sub n, and they want me to find G sub 11. Okay, so I'm going to do G sub 11 over here on the side. We have 48 times 1/2 to the power of 11 minus 2. 11 minus 2 is 9. When you have a fraction raised to an exponent, you need to do 1 to the 9th power and 2 to the 9th power. So you're going to do it to both of them. I'm going to convert 48 into a fraction by putting it over 1. You don't have to do that. I just do that because it helps some of my kids to put it over 1. But if you can do it in your head, that's perfectly okay. 1 to the 9th power is 1. And earlier we did 2 to the 9th power. So let me scroll back up and find my exponents. 2 to the 9th power is 512. So I'm going to put that down here. 2 to the 9th power is 512, and if I multiply straight across, I get 48 divided by 512. Now that is a big fraction, so we're going to have to simplify that, okay? Now, off the top of your head, you might not know the greatest common divisor. If you don't have the greatest common divisor, it is not the end of the world. It just means you might have to simplify 2 or 3 times before you get the most simplified answer. So I know what the greatest common divisor is, but I'm going to show you what it looks like when you do not have the greatest common divisor, okay? So let's just say I'm looking at this and I'm like, yeah, I think they're both divisible by 4, okay? So this is just an example. So then on the side, I'm going to have to do 48 divided by 4. I get 8, I get 12. So this equals 12. And then I'm going to do 512 divided by 4. I get 5 minus 4 is 1. Bring down the 1. You get 4 times 2, which is 8. 8 minus 2 is 3. Bring down the 2, and you get 8. Okay, so 12 over 128. You can tell that that is still not fully simplified. So now I'm going to divide again. So let's say I have 12 over 128, and then I'm like, I think they're still divisible by 4. So I'm going to try that again. 12 divided by 4 is 3. And then 128 divided by 4 would be 32. Okay, so I'm like, yeah, I think that's fully simplified because 3 is a prime number, so nothing is going to divide into 3. So the final answer is 3 over 32 for the 11th term. Okay, so here actually the greatest common divisor was 16. So 4 times 4, that's how it ended up being 16. That would be hard to do, 1, without a calculator, and 2, we're really only taught our times tables, our multiplication, until 12. So a lot of us don't know past 12. Some of us learned the 13's times tables, but most of us did not learn past 12 or 13. So off the top of your head, it would be very difficult to know that these are both divisible by 16. But again, it's not the end of the world. It just means you need to simplify 2 or 3 times until you get the most simplified answer. Okay, but this is it for this lesson. If you guys have any questions, please let me know in the comments below, and I will see you in the next video. Have a good night. Bye.